Hi everybody, I am John Suárez, a PhD student from the University of Los Andes in Bogota, Colombia, and I will talk about our research assessing the quality of massive spectroscopic surveys with unsupervised machine learning. This research is part of my thesis project with my advisor, Jaime Forero, and the DESI collaboration. First, I will talk about DESI. DESI is the Dark Energy Spectroscopic Instrument, a collaboration where more than 70 international institutes participate. This experiment is managed by the Lawrence Berkeley Laboratory in California. So the instrument is installed in the Kitt Peak National Observatory in the Tucson Desert in Arizona. The main aims project is to study the nature of the dark energy in the universe. The construction of this instrument began in 2015, and the first observations were made in the second semester of 2019. The main idea behind this is to obtain the biggest universe map. For this, a total of 40 million of spectra will be measured in a total field view of 14,000 square degrees. The objects that will be observed in DESI include galaxies, quasars, and stars. This map will be the key to constraining parameters in the dark energy models. In contrast, the Sloan Digital Sky Survey, that is the predecessor of DESI, only has measures to a redshift of 0.5. DESI will observe a redshift of 2 or more. This figure illustrates this situation. Each point in this figure is a galaxy. The black region is the region observed by the DSS, and the purple region will be the region that DESI will measure and includes the region observed by the Sloan Digital Sky Survey. So, how are measured the spectrum in DESI? DESI is a new generation of telescopes. For this experiment, there are a total of 5,000 automatic positioners. These positioners have fibers that capture the light from the galaxies. These fibers have a length of 40 meters and are connected to 10 spectrographs. These spectrographs split the light into three spectral bands, the B, the R, and the Z band. The spectra are measured in a wavelength range from 3600 to 9600 angstroms with a resolution from 2000 to 5000 that depends on the wavelength. The field of vision of one observation is 8 square degrees. This is a petal with 500 positioners. 10 petals like this have a total of 5,000 positioners that measure the same number of spectrum in a unique observation. This is the galaxy light that enters into the telescope. The light is reflected by the primary mirror on a set of lenses that projects the light on a focal surface where are located the positioners. The light is captured and split by bands and measured in a CCD camera. Each piece in this instrument could be a source of errors. These are the 10 petals configuration with a total of 5,000 positioners available to capture the light from 5,000 sources. It's an example of the spectrum from the Triangulum galaxy. This fiber located in this petal captures the light from this galaxy. Then the light captured is processed to obtain a spectrum like this one. This is a concatenated spectrum from the three spectral bands, the B, the R, and the C band. This is the common acquisition process. First, we observe the sky. It is an instrumental step. Then we make the corrections and calibrations with a reduction pipeline. Finally, we obtain the final calibrated spectrum. In each step of this process, it's possible to find instrumental or reduction errors. So the problem is to find these errors. In an experiment like this, the problem is harder. So we need to measure the quality of a big amount of spectra in a short time. To solve this problem, we propose a solution based on unsupervised machine learning. We use the UMAP algorithm, or the Uniform Manifold Approximation and Projection algorithm. This is a nonlinear dimensionality reduction and also is used for visualization tasks. Also, this algorithm has applications for outliers detection. A difference of other dimensionality reduction algorithms, like the popular PCA, UMAP builds a neighbor graph in the original space of the data and tries to find a similar graph in the lower dimension space. In comparison to another graph-based dimensionality reduction, like for example TSNE, UMAP is faster due to its optimizations and strong mathematical foundations. Also, another advantage of UMAP is the improvement in the balance between the locality and globality clustering. This is a real-world example. The inputs are figures handwritten with numbers from 0 to 9. Each figure has a dimension of 64, is a 8 times 8. Then, using the UMAP algorithm, it's possible to obtain this two-dimensional reduced projection. The numbers are clustered by class. Each island contains similar objects. In this example, we can see that the number 1 is located in this island, the number 2 in this island, but we can identify that some outliers are far from each island. For example, these outliers that are the number 1 are far from each island. In our case, we have that data that are spectra. The first results from the DESI collaboration were the anti-reduction pipeline. This is an example of one spectra from an observation on March 2020. This reduction pipeline contains 22,000 spectra, is one with a length of 2,000 points. 6,000 points if we consider the three spectral bands concatenated. We use the UMAP algorithm on the data from the Andes data release and project this spectra into a two-dimensional space. In this plot, the blue points are galaxies, the purple are quasars, and the green points are stars. In this projection, we can identify some islands. For example, this large green island means that the stars that compose this one share similar features. Also for this island of quasars. The UMAT algorithm has some tunable parameters. The number of neighbors is a parameter that controls the number of objects in the input space that UMAP used to project. It means that low number focus on the local structure while high numbers focus on the global structure. The minimal distance is the second parameter. This parameter controls the distance of the objects in the output space. It means how tightly the algorithm will map into the output space. The metric, that is the third parameter, is used to measure the distance in the input space. The dimension parameter fixes the final dimension of projection. So we explore these metaparameters using different intervals. For the number of neighbors, we use values from 0 to 50 in steps of 5. A minimal distance from 0.0 to 0.5 in steps of 0.1, and three different metrics: an Euclidean metric, a cosine metric, and a Breit-Curtis metric. Then we use the output of the UMAP algorithm as an input for a friend of friends algorithm to identify the islands. For this, we tune the linking length metaparameter in a step of 0.1 from 0.1 to 0.5. The first experiment showed us good results. We use our method in the data from 14 March 2020 with these parameters. the cosine metric and number of neighbors equal to 15, a minimal distance of zero point 0.5 and a linking length of 0.1. In this projection, we identify this island. These spectra share the similar feature, large negative flux. We report this error to the DESI data group that identified this error as an instrumental error. It means a defect in the CCD camera. Also, this is another example from a posterior data release for the Denali data release. It is from a night on January 2021. The DESI community that works in visual inspection identifies some spectra like rare. Then we use our method and find that these rare spectra are located in this island. Also, this feature was identified by the DESI data group as an instrumental error. It means contamination in the observation process. The metaparameters that we use for obtain this projection were a cosine metric also, a number of neighbors equal to 15, a minimal distance of 0.5, and a linking length of 0.2. Here we only change the linking length in comparison with the previous results. Finally, we can conclude first that our learning-based method using UMAP and friend-of-friend is a good strategy for assessing the quality of massive spectroscopic surveys. The examples that we showed here demonstrate the power of our method. Also, we can conclude that our method is promissory to detect outliers and also could be added to the pipeline reduction as an early alert system to identify some instrumental errors. Finally, we are confident that this mechanism could be implemented in future surveys like the WIF survey, the Subaru PSF, Foremost, Euclid, and other surveys to assess the quality of massive spectroscopic surveys. So, thank you. If you have questions or comments, please write me at this email.